Spacetime is special because it combines space and time into a single four-dimensional entity. And we've seen that we can draw spacetime diagrams and light cones to show events in spacetime. What we're going to do now is to see some special properties of spacetime diagrams which will help us to understand how things move and interact in spacetime. We're going to look at how we measure the interval between two events in spacetime. In Euclidean space, that we might call 2D or 3D pure space, we can all agree on what the shortest distance is between 2 points. We know the shortest distance is a straight line, and its length can be calculated using Pythagoras' theorem, whether in 2 dimensions or 3 dimensions. This shortest straight line distance is something that all observers agree on, so we can call that a distance which is invariant, meaning it does not change no matter who is looking at it. This straight line distance is invariant only in Euclidean space because there, as defined by Isaac Newton, there is the notion of absolute space and absolute time. But we know that this isn't the complete picture because time and space are not absolute or independent, as we have seen in our videos of relativity theory. Before we look at what happens in space-time, let us just recall some things from special relativity which will help us understand what we're going to do in space-time. If Alice is moving along the x-axis at speed v relative to Ben, then we can say that Alice has her inertial frame of reference, the car, and Ben has his inertial frame of reference, the ground. Alice and Ben's frames of reference are connected to each other by what is known as the Lorentz transformation. And this Lorentz transformation tells Alice and Ben how to move from one frame of reference to the other frame of reference. If the space and time coordinates for Alice are xa, ya, za, ta in her frame of reference, and for Ben they are xb, yb, zb, tb in his frame of reference, then the Lorentz transformations can be written like this, where gamma is the Lorentz factor we've seen before. This Lorentz transformation allows Ben and Alice to convert each other's measurements of distance and time into their own frames of reference. But, crucially, Alice and Ben do not agree on distances and times under a Lorentz transformation. We say that distances and times are not invariant under a Lorentz transformation. In fact, the only thing which Alice and Ben both agree on is the speed of light. So we can say that the speed of light is invariant under a Lorentz transformation. That is, all inertial observers agree on the value of the speed of light no matter how they are moving. That is okay for the speed of light, but we usually like to work with distances and times. So what we're after is finding a quantity on which all observers can agree on when a Lorentz transformation is applied. It turns out there is such a quantity in space-time, and it is called the space-time interval. This really is a fundamental quantity to understand when dealing with space-time, and we will now see what it is. Let's start with our space-time diagram, and we will draw one space axis horizontally for x and a vertical time axis. We want to do useful calculations in space-time using these two axes, but it should be obvious that currently the two axes are different. One has units of time and the other has units of distance. We can't really work with these different units because any relationships we want to find between the time and space axes must have consistent units. To overcome this problem, what we do is to change our time axis so that it has units of distance. What we do is to multiply time by the speed of light, so we get ct on the vertical axis. Since the speed multiplied by time gives a distance, ct gives us a measure of distance. We can do this because the speed of light is constant for everyone. And so this is like multiplying the time axis by a constant number. It really is just a change of scaling factor, but it allows us to have units of distance on both axes. Hence, we can then do calculations in our space-time diagram because we'll be dealing with units of distance on both axes. You might be wondering what the actual units will be on the time axis. Well, quantities like light years, light minutes, and light seconds are actually measurements of distance, the distance that light travels in a certain time. So light travels a distance of 1 light second in 1 second. We can define it like this because the speed of light is a constant. Hence, instead of using meters per second for the speed of light, if we can state the speed of light in light seconds per second, then c times t will give a unit of light seconds. So the time axis takes on units of light seconds, and now we have our space-time diagram with one axis x and the other axis ct, and we can carry on since everything is now in units of distance. Suppose there are two events in space-time, p and q. What we want to work out is the interval in space-time between the two events, and we can call this the space-time interval, ds squared. The space-time interval, ds squared, is given by the equation ds squared equals dx squared minus ct squared. If we compare this to our more usual view of the distance between 2 points in Euclidean space, then we can see that the obvious difference is that there is a minus sign in the space-time formula. This minus sign is an indicator of why space-time is different, and let's see what our space-time interval formula implies. As we've seen, a moving Alice and static Ben will only agree on the speed of light. So what happens when each one measures the speed of light in their own frames of reference? Alice will say that distance moved xa divided by time ta will equal the speed of light, and Ben will say the distance moved xb divided by the time tb equals the speed of light. We can then rearrange these equations and we get the relationship shown. So the minus sign comes about because in space-time all observers have to balance distances and times such that the speed of light is always the same. And this can only be done if distances and times have opposing signs. If you move more in space, then you move less in time, and vice versa. And in all cases, the speed of light must remain constant. ds squared, as given by this formula, can have three types of values. ds squared can be negative, it can be 0, or it can be positive. These three states of the space-time interval give us three categories of travel in space-time, so let's look at each of these three categories. Before we start, for completeness, let us show all three axes of space, so our equation for ds squared becomes this. The sum of the x, y, and z squared terms is just the square of the distance in space, so let's call that delta r squared. So we now have delta s squared equals delta r squared minus c squared t squared. So the space-time interval is the distance squared minus the time interval squared in units of distance. The first case is where space-time interval ds squared between events is less than 0. If ds squared is less than 0, then that means that the spatial distance dr squared will be less than the time interval. Remember, what we are talking about is ds squared, which is the space-time interval between two events. The spatial separation dr between two events can never be negative, so the minimum value it can have is 0. And this means that due to this inequality, dr squared is less than c squared delta t squared, dt can never be 0. It must always be positive. And that means that no matter what reference frame an observer is looking at these two events from, that observer can never find a reference frame where the time interval is 0. There is only one reference frame where dr is 0, and even in that case, the time interval would still be more than 0. So the conclusion is that there exist no frames of reference where the time interval is 0. In all cases, when ds squared is less than 0, there will always be some positive time interval, delta t, and so this case of ds squared being less than 0 defines what are known as time-like intervals. In the case of two events such that the spacetime interval ds squared is more than 0, this means that the spatial interval dr squared is more than c squared dt squared. dt squared can be 0, but can never be less than 0. So this means that dr squared must always be more than 0. So no matter what frame of reference an observer looks from, there will always be some spatial interval between the two events, since dr squared is always more than 0. And hence the case of dr squared being more than 0 defines what are known as space-like intervals. For the final case, where space-time interval ds squared between two events equals 0, this means that the spatial interval and time interval are connected by the speed of light, with dr squared equal to c squared dt squared. What this means is that if there are two events, then they are connected by a photon of light going from one event to the other event. The light sets off from the first event, and the second event occurs when the light reaches it. So the case where ds squared equals 0 defines what are known as light-like intervals. In terms of a space-time diagram with a light cone, we can display these three cases like this, showing the time-like intervals inside the light cone, the space-like intervals outside the light cone, and light-like intervals always being on the edge of the light cones, defining where light, and only light, can travel. We said earlier that a space-time interval is an important quantity because it is invariant under a Lorentz transformation. That is, all observers agree on space-time intervals no matter what their frames of reference are. Let's prove this by looking at doing a Lorentz transformation between Alice and Ben, where they are measuring space-time intervals in their frames of reference. Using Alice and Ben's frames of reference, which we saw earlier, we can write the space-time interval as measured by each of them like this. What we're saying is that both Alice and Ben should agree on the space-time interval, so we can say that these two expressions should be equal. We know that a Lorentz transformation can be used to convert one frame of reference to another, so we will apply the Lorentz transformation to Ben's frame of reference and see what that gives us. To keep things as simple as we can, we will just take the case we saw earlier, that of Alice moving only in the x direction with respect to Ben. We could do the following calculations if Alice was moving in all three dimensions of space with respect to Ben, but it would get unnecessarily complicated. So we will just show the case of motion in x. We won't go through this proof in detail, but feel free to pause the video if you want to examine the steps for yourself. What we have shown in this calculation is that Alice and Ben measure the same space-time interval in their own frames of reference, meaning that space-time intervals are actually invariant under a Lorentz transformation. The result of all this is that in space-time, the only things which are invariant are space-time intervals and, as always, the speed of light. And that's a good place to leave space-time intervals for now. Hopefully you have followed along and seen how the constant nature of the speed of light leads to the fact that space-time intervals do not change when measured by two inertial observers. If there are two events in space-time, then all observers will agree on the space-time interval between the two events, even if the observers are in different frames of reference and moving with respect to each other. The crucial point is that observers moving relative to each other do not agree on individual times or individual distances, but they always agree on the combination of times and distances as defined by a space-time interval. In the next video, we will continue looking at space-time diagrams by seeing how we can obtain further insights about effects in space-time. I hope you'll consider subscribing to this channel, and until next time, keep thinking physics.